We have seen and calculated how much pencils to order for our bookstore and when to reorder also. And now you might wonder why the economic order quantity is so famous and well used in practice, which I will show you now. Our cost function that we apply is quite insensitive to errors made in the order quantity. So in order to show you that, we need to derive here an expression for the ratio of the suboptimal and the optimal order quantities. And therefore we will use our cost function and combine it together with the optimal order quantity. So that is now our Q. And we will get this term when we do so. For those who don't recall mathematics so far at that point, I will show you now how to come from this term to that term. For the purpose, we use the whiteboard and we take our cost function. I call it now G. It doesn't matter. Beforehand in the previous lecture slides we called it zeta of Q. So that is the same. Sorry about the denotation that changed, but it doesn't matter. So this is our cost function. And now you will see, we set in the term for the optimal order quantity. And this doesn't look too easy, so we use Algebra to rearrange the terms. So on this side, I say multiply by 2 to make things easier, and for this term, I multiply by the optimal order quantity, which is fine if we do it for the whole fraction. You will soon see why I do this. So if I multiply here this term 2 times, then I lose the square root. And I add it in the denominator. And you see that here we get rid of the h. And you see that now we have the same denominator here, so we can bring these two together. And now here we can, in the denominator, we can also make things a little bit easier. So here we lose the 2. And this this what I wrote here. Of course, we can, this term is kd plus kd is 2 times kd. So it's 2 times k multiplied d. And this is still 2kd divided by h in square root. This doesn't look too good still. So we continue. Now I do it step one by one. Here you see we have a kd in the square root and a kd in the denominator. What we can do to these things, we put, we lose a little bit the square root. Every of our input parameter can be taken isolatedly in the square root. So, and then step by step we put the h here. So because you have here the denominator and here another fraction, then the h can be rearranged. And then, well, we want to do something with our kd here, and we have a 2 here as well. So we can work with this to make it look nicer. So here stands 2kd, and I can reformulate the fraction here, which is actually 2kd. So the square root is exponential a half, and if it stands in the denominator, then it's minus. So it would be minus 1 plus 1 half, and that is, and we leave our h in the square root. And now you see that here we can ease things. So if we take here, you recall that for every parameter we have 1 in the exponential. We don't write it, why should we? But if we lose the, I make it more straightforward. We can actually write it for each and every term. Just very extensively now. So here stands 2, 1, and here we have another 2, so we can just subtract the exponents from them, and we do the same for kd. I do it together because it's the same for these two. And we should not forget our h and the square root. So this here is minus a half. Sorry. That is a half, of course. So we have here 2 exponential a half multiplied by kd a half, and our square root h. And well, this is nothing else, and the others as well, or we can express them as square root of 2. So we can put them all together in square roots, and then this becomes 2 times k multiplied k multiplied d multiplied h in 1 square root. And this is what we have in our lecture slides, which is this term. Now you know how to derivate this term, or how to come to it. And now we do the same for the ratio of the suboptimal and the optimal order costs. So this is where we start with, and we want to arrive here. If you know how to do it, then of course you can skip this part. So we take now the optimal cost, or the cost function, divided by the optimal costs, and this is the following expression. This divided by the term that we just have derived. It doesn't matter if you put a multiple in between or not. Sometimes I do it and sometimes I don't, so please don't get confused on this. Here I didn't do it. So first thing that I want to do is here we have a sum. So to rearrange the terms, I want to divide these two fractions from each and another. So I put them alone on a denominator, then I can work with the two parts, the two terms alone. And now I want to simplify. So first thing that I do, I work with the denominator here and also here on the both sides. So I rearrange, and the square root is can be rewritten as follows. So we have it in the denominator. We can write it in the numerator by exponential -1. And the square root we lose with a half. So in total this becomes -1/2. Same thing for the second term. And now we look once again how we can rearrange things, and we see that here in our formula for the first term we have KD here, so we can simplify things on this side, and here we have our inventory holding cost factor H. So we rearrange the KD then becomes, this is -1/2 in the expressor, I hope it's called in English, and this is 1. So these two, I write it extensively, is 1 minus 1/2 for our 2h. We don't change anything, and this divided by h. Plus, and here the same, h is 1 minus 1/2 q, and 2 kd does not change, remains there. Still, it doesn't look too nice. So here this is 1/2. So we have here KD 1/2 multiplied by 2h 1/2, and this is h 1/2 multiplied by q 2kd 1/2, and then nothing has changed. I forgot our H here, our Q. We can write the first term now. Another thing that I will do now is I multiply this term by 2. So this overall term I multiply by 2. You will soon see why I do this. If I do so, then because I want to lose or to get rid of the 2 here, and you will soon see why. So I multiply the term by 2, and I rearrange a little bit so I can work here with this. This is 2 minus a half, and the H also, I don't need the bracket, but anyway, this is the same. And now here I can ease 2.5 minus a half kd a half, and now things become more clear, hopefully. If we now rearrange the terms that we have, we can we put them in square roots, and then we get square root. The 2 and the kd are in the numerator, and the h is in the denominator. And I do the same here. I just spared writing it. I do the same for our second term. And you will see that this is, I put that also in square root, h divided by 2 kd. And now you should realize something. You should realize that this term actually is the expression for our optimal order quantity. And this one is the term just reversed. And if we write that nicer, then we get Q denominator plus 1/2 Q like this, and we can still rearrange the expression into the following ratio. We have now the following request for our bookshop. We should suppose now that the bookstore orders pencils in batches of 1,000 units. So the order quantity that they order is 1,000 units rather than the optimal 3,870 that we calculated. So what additional costs occur by using such a suboptimal solution or order quantity? For that purpose, we take the whiteboard again and calculate the costs that occur when using or when ordering the 1,000 despite the optimal order cost that we calculated. I rewrite the term, our formula, so our K was $12, our demand was 3,120 for the bookstore, and now we order, despite the 3,870, we order just 1,000 units. And now we have the inventory holding cost factor was 0.005. multiplied by the 1,000 that the bookstore orders, divided by 2, and this is $39.94, and this is quite larger than the cost that we had for the optimal order quantity. Just to recall, that were $19.35. If we now use this knowledge of our ratio that we have just derived, that was given as the difference, the ratio between the new order cost and the optimal order cost. In the formula, it's given as follows. So if we insert our data, and the optimal order quantity was 3,870 divided by the suboptimal order quantity. And this is 2.06. So our average costs now, when we apply a suboptimal order cost, is just 2.06 times larger than the optimal average order cost. So if you see the ratio here of the difference of ordering, then it's incredible to see that the order costs that derive from such a huge error is quite small. We can formalize what I just said and say, if our order quantity is twice as large so our ratio here is then the order cost is 1.25, meaning that 100% of error of the mistake in ordering too little just result in an, let's call it, ordering error of only 25%. For holding costs of inventory and our setup costs. Yeah, and this is quite surprising. So our economic order quantity is very, very insensitive to errors, and it gives very good results in what to order. And this is why this EOQ formula is so important and also so popular in practice. Here we have an exercise of a specialty in a coffee house that I would ask you to do as the next assignment. We go further to, this is the statement that we have just derived. And we go further now to extend our economic order quantity and relax the assumption of 0 lead times. So now we assume that despite, here we reorder when our inventory has dropped to 0. What happens now if we have a positive order lead time, so that we need to wait for our order to arrive. So we need to place our order before that. When the order arrives, then our inventory will drop to 0. So this is the time in between. When we relax the assumption, we can define a reorder point, big R. That is the level of on-hand inventory at the moment where we should place our order. That would be exactly here. When we have a lead time of this fraction, so this is here, and this we can rewrite as the demand multiplied by the positive order lead time. So the way to obtain the optimal order point is that we take the ratio of our lead time and the demand rate, and then consider only the fraction of this ratio. Sorry for the typo. And then multiply this fraction by the demand rate, or by the demand on hand, to have the reorder point. Good question is now, what happens if our order lead time is larger than our T? And I will show you now how we can derive the mathematical expression for that case. For this purpose, we take the whiteboard and we extend our graphic a little bit to regard more than one cycle. So we order quantity Q, and due to our demand rate, this drops to 0 at a point T. So this time we can define as T equals Q divided by the demand rate. And our assumption was that if we have 0 lead time, then when we order, we immediately have the inventory in store. Oop, that should not happen. So the assumption is that this circle, or this cycle would repeat itself over and over again, all the time the same cycle. This would be 3. I write now this is the mth cycle, so I can write m multiplied by t here at that stage. The assumption now of positive lead time is that here we would receive our order. And if we have a positive lead time, then we need to order this lead time beforehand at a certain stage. Let's assume that here this is the order lead time, or the delivery lead time from our supplier, and I denote it by a Greek tau 1. And then we can define the reorder point as R here. What happens now if our order lead time is larger than our T? So what happens in this case? And write that somewhere else because I need the space. So what if tau 1 is larger than tau? And we can define the this is from T to MLT, this is MT. And if we consider the positive lead time, then this is the extra T1 that we need to add to our MT. So our overall T becomes MT plus our positive order lead time. If we define now this order point here as A and the point in time here as B, then we want to know how much to order, so we need to consider this space, this one, and all the repetitions of the cycle. So we need to define the total demand. D in the interval now from A to B. And this is demand multiplied by the total time that we consider, that is this here. And then we would know how much to order. So since, and this we can rewrite then. So if we put this into this, then D multiplied by MT plus tau 1 is the total demand. If we rearrange the terms and we want to isolate the T, then we have Q divided by D. And this information here we can now insert into our function for the total demand. To derive the total demand here. And this is then D. I just repeat the formula for the total demand and insert our QD plus our time for the our order lead time. What we do now is we simply lose the bracket and here we get rid of the D. So this is now the function of the statement of the total demand in this interval that we consider when we have a positive lead time. So we know that we reorder Q units every time we place an order. Then we know that we have ordered already at that point Q units. And that means for the optimal reorder point with positive lead times, that would be multiplied by Q that we had already for the expression of the total demand at that point. And we know we have already ordered the MQ units, and that means that the optimal reorder point with positive lead times is the total or our demand rate multiplied by the positive order lead time. And that should make also perfectly sense, because we need to order exactly that fraction of our demand rate for our positive lead time in advance before our inventory drops to 0.